morning, everyone. The paper we will discuss today is the overview of the SPARC tokamak, Chapter 5, Investigation of SPARC Physics. In addition to the work described in Chapter 4, a number of other aspects of the physics of SPARC plasmas have been investigated in some detail. Each of these topics is detailed in another article in this series, but a brief description is given here. Since the design of ITER and the writing of the ITER Physics Basic, and the progress in the ITER Physics Basic, considerable advancements have been made in physics-based modeling of tokamak plasma. High-fidelity models now exist for core turbulent transport H-mode pedestals, energetic particle heating, as well as many other aspects of tokamak plasma. These advancements mean that one can now perform integrated modeling of many parts of the plasma in order to project the performance of a machine that has not yet been built, while SPARC parameters were initially chosen based on the empirical scalings used in the ITER design. Integrated modeling has been performed as part of the SPARC design process and is described in Rodriguez. This modeling predicts a peak performance of Q equals 9 for the full current, full field H mode in SPARC, which, given the considerable uncertainties in both the empirical scalings and models used here, is in remarkable agreement with the empirical prediction of Q equal 11. Such agreement reduces the risk that the SPARC operating regime is somehow qualitatively different from these used to generate the empirical scaling laws, and thus increases confidence in SPARC's performance projections. Peak performance in SPARC will likely require operating in H mode, so special attention has been paid to H mode accessibility and to the challenges that come with H mode operation, such as H localized models. While H mode has been accessed in nearly all modern diverter tokamaks, the physics of the LH transition is still an area of active research, and predictions of the power required to transition have considerable uncertainty. In addition, H localized models present a major challenge in many high power density devices, as they lead to considerable transient loading to the diverter and other surfaces. Both of these phenomena, as well as others, including the ability to maintain high-quality H-mode confinement and the implications of reduced pedestal quality, are considered in greater detail in Hughes. It is shown in Hughes and Rodriguez that SPARC is able to achieve its mission of Q bigger than 2, even with a 50% degradation in pedestal pressure compared to the nominal prediction. The high power density in SPARC V2 and other burning plasma devices means that one of the most difficult changes in the device is heat exhaust. As such, considerable work has focused on the performance of the diverter and its ability to operate successfully in full power DT discharge. The baseline design scenario for SPARC V2 is to sweep attached diverter strike point in order to spread the exhaust heat across the diverter target. Since strike point sweeping places strict requirements on power supplies and other systems, It is important to consider this operational scenario early in the machine design, such the ability to balance a performance perfect double null is uncertainty. The SPARC diverters are being considerably conservatively designed that operate in single null. SPARC operation will represent an extrapolation in the empirical parallel heat flux wide scaling. And some recent modeling predicts considerably wider heat flux wides in low plasma. For this reason, data from SPARC on the diverter heat flux wise scaling will be an important physics result and may help resolve the differences between empirical scaling and modeling predictions. This conservative approach to design does not preclude the exploration of detached diverter regime. And SPARC will be able to test predictions for the impurity fractions required to induce detachment. Two-dimensional fluid modeling work has also been performed for SPARC to gauge the possibility of detachment. Diverter physics studies on SPARC will inform the design and operation of ARC's diverter, including the possibility of testing an advanced X-point target diverter configuration. SPARC's high field and current density place it in a somewhat unique operating space compared to other high-performance tokamak regimes with regard to MHD, while beta-driven instabilities are expected to play a significantly smaller role than in many current devices. The very large plasma current density leads to special concern around disruptions and the thermal and mechanical loads that these will place on the device. Electromagnetic disruption loads have been calculated based on empirical scalings, and SPARC's mechanical structures are being designed to withstand these loads. Main chamber plasma facing components are being designed to withstand anticipated radiative heating during disruptions, including appropriate peaking factors. The effects of disruptions, specifically on the diverter, are considered further in Kuang. In addition, the generation and mitigation of runaway electrons in SPARC have been considered building on earlier work that analyzed SPARC V0. The possibility of incorporating a passive non-asymmetric coil in order to reduce the likelihood of damage from a runaway electron beam is also under consideration. The high field and high density in SPARC make ICRH the preferred source of auxiliary heating, since SPARC will rely exclusively on ICRH. Considerable work has been put into determining the efficacy of various ICRH operating scenarios and systems. Depending on the operating field, either a hydrogen or helium-3 minority will be the primary species into which power is deposited. heating of fast alpha particles is predicted to be small and minority tail energies should not be problematic. The ICRH, power source, transmission, and antenna systems have also been scoped out based on existing equipment such as that from Allocator C mode. Finally, one of the most novel areas of SPARC physics will be the presence of large populations of alpha particles. Care must be taken to ensure that alphas will not damage the device, and detailed neoclassical and rippled loss simulations have shown that first wall heating from alpha losses from these mechanisms should be modest with a 0.3% toroidal field ripple in SPARC V2 ripple in induced alpha losses are projected to the less than 1%. The possibility of interactions between alpha particles and high-frequency MHD modes is an area of interest, and initial examination of the effect of high-field operation in general on alpha-bin agent mode liner stability has been carried out. This work suggests that the SPARC regime of alpha physics as close to that has been predicted for ether, since the ion temperatures are similar in addition to MHD interactions. SPARC should also be able to explore various other aspects of alpha and burning plasma physics, including alpha stabilization of turbulence, the interaction of alpha populations with shorties, and the self-consistent plasma profiles that result from dominant alpha heating, the self-consistent distribution of alphas in space and energy in high-gain plasmas is a frontier research topic, and SPARC will expand upon earlier work from TFTR and JET. Thank you for listening to the end of today's show.